Have you ever found yourself on the train platform checking your watch, only for that dreaded announcement to come over the loudspeaker? Your train is delayed.
Oh, yeah. We've all been there.
We've all experienced it. Or conversely, perhaps you've noticed that some of the newer train lines or even the latest models of trains just seem to run flawlessly with fewer unexpected hiccups.
Definitely. Especially compared to older systems that always seem to have the same issues cropping up again and again. It really makes you wonder.
It does. Why do some complex systems like an entire railway network actually seem to get better, more reliable over time, while others just, well, don't?
Right.
It's not some kind of mysterious magic or just blind luck. It's a very deliberate, systematic, and frankly fascinating engineering process known as reliability growth. And here's what I find surprising about it. It means complex machines don't just passively wear out. They can be actively engineered to become smarter, more robust, and safer over their entire lifespan.
That's absolutely right. Today, we're going to take a deep dive into precisely how railway systems, and really many complex engineering systems, are intentionally designed to improve their reliability throughout their operational lifespan.
Okay.
We'll explore the very practical, hands-on steps that engineers take on the ground to make this happen, essentially, building reliability into the system.
Right.
And then we'll pull back the curtain on the clever mathematical models that not only allow us to measure and predict this critical improvement, but also help us actively manage it, turning raw data into powerful insights.
Our mission today is really to unpack this entire journey a system takes. From its initial deployment, when, let's be honest, some unforeseen flaws are almost always present.
Always. It's expected, almost.
All the way to a state of high, stable reliability. We want to give you, our listeners, a shortcut to understanding the core concepts and the very practical applications that drive safer, more efficient, and ultimately more predictable railway operations.
It's about turning potential chaos into predictable excellence, really.
Exactly. So what does this all mean for the future of transportation, and why should you, maybe someone just starting in an engineering field, or even just curious about how the world around you works, care about this seemingly abstract idea of reliability growth? Let's unpack this.
Let's do it. Let's begin by defining what is reliability growth. At its core, it's a process where the reliability of a system, whether it's a single train, a complex signaling network, or an entire railway line, demonstrably improves over time.
Demonstrably. That's key.
Yes. Now, this is important. It's not just about the simple act of repairing a broken component after it fails. That's reactive.
Right, like fixing a flat tire.
Exactly. You fix it, you're back on the road. But reliability growth goes far beyond that. It's fundamentally about proactively and systematically identifying the root causes of those failures.
The root causes.
Implementing targeted corrective actions based on those causes, and then, crucially, preventing those specific failures from happening again in the future. It's about learning and evolving the system itself.
So it's not just a Band-Aid solution then. It's about getting to the fundamental why behind the problem, right? Understanding the deep-seated issues.
Precisely.
And this process is especially critical during those initial test periods, I imagine, or the qualification phases before a system goes fully live.
Absolutely critical.
Or even its very early operational life when engineers are still, working out the kinks of a brand new system.
That's when it's most intense. It's when a system is raw and new and you're looking for every opportunity to make it better, to harden it.
So the big questions on an engineer's mind must always be, if we fix this, what will the actual impact be on overall reliability? And what's the absolute best level of reliability we can realistically achieve with our current methods, and how quickly can we get there?
Those are exactly the questions. And the importance. Well, for you, the passenger, it's immediately clear. It means fewer delays, safer journeys, and a much more predictable service.
Something you can actually rely on.
Imagine a train schedule you can genuinely rely on, day in and day out. That's the goal. And for the engineers, the designers, the operators, this translates directly into significantly reduced maintenance costs, a massive boost in operational efficiency, and of course, a profoundly enhanced safety record.
Which is paramount in railways.
Absolutely. Every single failure, no matter how minor it seems, costs money, wastes time, disrupts service, and especially in railway systems, potentially puts lives at risk. So the drive for reliability growth isn't just a nice to have, it's an absolute imperative. It's a core component of responsible engineering.
That brings us to the how, because reliability isn't something that just magically appears or happens by accident.
Not at all.
It's truly engineered through meticulous effort and a really disciplined approach. The core principle of this proactive approach, as you said, is that failures and faults must be actively and rigorously detected.
You have to find them first.
You simply can't fix what you don't know is broken, or, perhaps even more importantly, what you don't know is about to break. You need to be listening to the system, anticipating its needs almost.
That's where the detect, analyze, implement cycle comes into play. It's a continuous feedback loop that really powers reliability growth. Let's break it down a bit.
Okay.
First, detection. This isn't limited to outright catastrophic failures where something completely stops working. That's obvious.
Right.
It also includes capturing what engineers call near-fault situations, those moments where something almost went wrong.
Ah, the close calls.
Exactly, where a component nearly failed, or a system briefly flickered on the edge of malfunction. Think of a train door that briefly sticks before closing, or maybe a signal light that momentarily flickers erratically.
Okay, those little anomalies.
Those near misses are invaluable data points. They're often detected through a whole variety of means. Onboard sensors constantly monitoring performance metrics like temperature, vibration, current draw.
All the vital signs?
Mm-hmm. Diagnostic software flagging unusual patterns. Even human observation from drivers or maintenance staff reporting subtle things they noticed. The goal is really to cast a wide net and capture every whisper of a problem before it screams.
So once a fault, or even a near fault, is detected, what's next? You move to analysis.
Yes, analysis. And this is key. Engineers don't just patch it up with a quick fix. They embark on an in-depth root cause analysis.
Getting to that why again.
Precisely. This process goes far beyond just identifying the failed component itself. It means meticulously looking at the entire life cycle of that component or system.
The whole history.
The whole history. Was there a flaw in the initial design? Maybe a miscalculation of stress on a particular part? Did a manufacturing error creep in during production, like a weak weld or maybe an incorrect material was used?
Could be anything.
Could be. Perhaps it was an issue during the testing phase, something missed, or even incorrect installation by a technician. It could be procedural.
So how do they trace that back? What techniques do they use?
Well, they might use techniques like the 5 whys, where you repeatedly ask why until you get to the fundamental issue. Or they develop fishbone diagrams, sometimes called Ishikawa diagrams, to visually explore all potential causes related to materials, methods, people, environment, machines.
A structured brainstorm almost.
Kind of. And this phase often involves multidisciplinary teams. You pull in design engineers, quality control specialists, maintenance technicians, even operational staff to ensure every single angle is considered. The goal here is to dig deep, to move beyond the symptoms to the underlying disease.
So once that root cause is finally identified, what happens next? It's not just about applying a fix, as you said, it's more fundamental.
That's right. You're not just putting a bandage on it, you're performing surgery, as you put it earlier. Based on that thorough root cause analysis, specific measures are implemented.
Okay.
But here's the crucial distinction for reliability growth. These measures are designed to remove the cause of the fault, not just the symptom, the fault itself.
Right. Prevent it from happening again.
Exactly. For example, if a bearing is failing prematurely, a simple fix is just replace the bearing. Easy.
Sure.
But the reliability growth approach asks why it failed. If the root cause was insufficient lubrication due to, say, a flaw in the design of the grease port, then the corrective action isn't just replacing the bearing. It's maybe redesigning the port or changing the maintenance schedule to ensure more frequent, effective lubrication. The aim is to prevent future occurrences, to ensure that the exact same problem doesn't resurface down the line.
So it could involve quite significant changes.
It absolutely could. Design changes, software updates, hardware modifications, revised maintenance protocols, even new training for personnel. It's about systemic improvement, not just reactive repair.
And this isn't a one-off event, right? It's an ongoing systematic process. I like thinking of it like a continuous feedback loop, always getting smarter, always getting better. The system itself is learning.
Precisely. And there's a widely used, highly effective framework for managing this continuous improvement. It's called FRACAS.
FRACAS?
Yeah, it stands for Failures Reporting, Analysis, and Corrective Action System. FRACAS provides a structured, disciplined approach to reliability growth, ensuring that learning isn't accidental, but deliberate.
Okay, structure is important here.
Very. It emphasizes several key elements. First, reliability growth needs to be planned. You don't just cross your fingers and hope for improvement.
Mm-hmm.
You establish explicit goals, targets for reliability, and strategies for improvement. Often you set specific phases with expected reliability gains.
Measurable goals.
Measurable goals.
Yeah.
Second, system reliability needs to be constantly observed and monitored, and specific indicators must be computed to objectively track how reliability is changing. You need to know if you're actually moving the needle.
You need the data.
You need the data. And third, active reliability management must be installed. This isn't a passive exercise. It's about actively managing the entire improvement process, often through regular FRACAS review meetings where data is scrutinized, problems are assigned, and solutions are tracked meticulously.
So it's about being proactive, not just reactive. What does that active management entail on a very practical day-to-day level for an engineering team? What does that look like?
Well, active reliability management ensures several critical things. It requires the meticulous registration and detection of all faults and those near-fault situations we talked about.
Everything gets logged.
Everything. Every anomaly, no matter how small, from a flickering light to a slightly elevated temperature reading, becomes a piece of the puzzle and is logged into a central database, usually the FRACAS database. And this data capture needs to be robust and standardized across the entire operation.
Consistency is key.
Absolutely. It also mandates that in-depth analysis of these faults, including that thorough root cause analysis. This means scrutinizing the entire life cycle of the system, from design analyses through production processes and into the testing phases, to uncover any underlying flaws.
Looking everywhere.
Everywhere. Are there issues in the specifications for parts? Is there a vendor quality control problem? Were assembly line procedures robust enough? The aim is always to improve the processes themselves the very way the system is designed, built, and maintained, not just to fix an isolated error.
So it's improving the whole ecosystem around the component.
Exactly. For example, if a new type of switch repeatedly fails, the FRACAS team might decide to not only replace the switch, but also maybe reevaluate the supplier, change the switch's design entirely, or even revise the electrical load calculations for that circuit if they find it was underspecified.
That makes perfect sense. And I imagine that when you implement a fix, especially one that involves a design change or a software update, you have to be incredibly careful not to inadvertently introduce new problems.
Oh, absolutely.
It's that classic whack-a-mole scenario, isn't it? Where fixing one thing causes 3 new issues to pop up somewhere else in a complex system.
Yeah.
How do engineers prevent that nightmare?
You've hit on one of the biggest challenges, definitely. And it's precisely where a functioning change management system becomes absolutely vital. This includes rigorous impact analysis and regression testing.
Okay, change management.
So when a fault cause is identified and a fix is developed, say a revised component or a new line of code for a control system, that fix is not just deployed haphazardly.
Right.
It's treated like a formal change to the system, like a carefully choreographed move in a dance.
I like that analogy.
It means it first undergoes a thorough impact analysis. Engineers evaluate what other parts of the system might be affected by this modification. Will this new component fit correctly with existing interfaces? Will this software patch affect the timing or functionality of other interconnected systems? Does it require new training for maintenance staff? This analysis prevents those unintended consequences.
Thinking through all the ripples.
Exactly. Then, crucial for preventing that whack-a-mole scenario you so aptly described is rigorous regression testing.
Regression testing, what does that involve?
It involves running a comprehensive suite of tests to ensure that the implemented fix didn't inadvertently introduce new bugs or, importantly, reintroduce old ones that were thought to be resolved.
Making sure old ghosts don't reappear.
Precisely. It's like checking every single domino in a chain to make sure that fixing one wobbly domino hasn't made another one unstable further down the line.
Right.
This can involve extensive simulation, laboratory testing under various conditions, and even controlled field trials on a limited number of units before a change is rolled out across an entire fleet or network.
So it's quite involved before it goes live.
Very. The impact analysis also dictates which existing tests need to be repeated and which additional new tests might be necessary to fully validate the change. It's all about building confidence, ensuring that every step forward doesn't inadvertently lead to 2 steps back.
That's a great analogy, actually. Like debugging a really complex piece of software. You don't just fix a crash. You trace back why the crash happened, maybe update your coding practices or standards, test the fix itself, and then, vitally, retest all related functionalities to ensure you haven't introduced new bugs.
Exactly the same logic.
It's that systematic, disciplined logic that railway reliability growth truly follows. It's not just fixing, it's learning and evolving, a continuous cycle of improvement, It takes incredible human discipline, really.
It really does. And all that discipline generates data mountains of it, potentially, on every single fault and fix, every near miss. And for engineers, that data isn't just a historical record. It's the raw material for something truly remarkable. The mathematical models that can tell us not just where we've been, but maybe where we're going.
That's fascinating. So once you have all this meticulous data, how do you translate that into something concrete? I imagine intuition alone isn't enough to really grasp if things are truly improving, or certainly not enough to predict future performance accurately.
Not at all.
You need quantifiable data and robust models to make truly informed decisions, especially when safety and operational efficiency are on the line.
Absolutely. Think about it. Traditionally, when we consider a machine failing, we might imagine something simple like a light bulb. It's installed, it works for a while, and then poof, it fails and you replace it.
Right, one life.
One life. Its lifetime can often be described by models like the exponential distribution, which assumes a constant failure rate over its operational life. That's a one-and-done scenario.
Okay.
But a train or a railway signaling system isn't a light bulb. It's a repairable system. It fails, it gets fixed, maybe improved, and then it keeps going.
Right.
And ideally, after a proper fix, especially one that addresses the root cause through this reliability growth process, it should perform better than it did before.
To learn something.
Exactly. So those simple one-and-done lifetime models, while useful for certain non-repairable components, don't really capture the dynamic, improving behavior we're talking about with reliability growth. We need a model that understands learning and improvement over time for systems that keep operating after repair.
So if those traditional models aren't enough for these complex repairable systems, what do engineers use? What kind of mathematical framework allows for this dynamic improvement?
This is where the non-homogeneous Poisson process, or NHPP, becomes incredibly powerful.
NHPP.
It's a sophisticated statistical tool specifically designed for systems that generate a flow of faults over time, especially when that flow changes in intensity.
Changes in intensity, meaning the rate of failures changes.
Precisely. Think of it this way. A simpler model, the homogeneous Poisson process, or HPP, is used for repairable systems where failures happen at a constant rate, like a very mature system that's just ticking along, experiencing random failures, but not really improving or deteriorating significantly.
Okay, steady state.
Steady state. The NHPP is a generalization of that. It allows that failure rate, or what we call the rate of occurrence of failures, to change over time, which beautifully reflects a system that is either improving, rate going down, or unfortunately deteriorating, rate going up.
So the key idea here is the ROQF, the rate of occurrence of failures. It's not just about how many failures you have, but how often they occur at any given point in time. So if a system is truly improving, its RQ should be decreasing, right? Fewer failures happening over the same amount of time.
Exactly. If the RCOF is decreasing, it means failures are becoming less frequent as the system ages and as fixes are implemented. This is the clear mathematical signature of genuine reliability improvement.
Makes sense.
The NHPP is built on a few statistical ideas that make it perfect for tracking this. Essentially, it allows us to model a situation where the probability of a failure occurring in any given small time interval changes over time. It assumes, generally, that failures happen independently and one at a time, which is often reasonable for complex systems between major overhauls. And it's flexible enough to show a system improving, deteriorating, or just staying steady.
So it transforms that raw list of when did something break into a curve almost that reveals the system's underlying health trend.
That's a great way to put it. Yeah, it reveals the trend.
So while the NHPP is the general framework, for practical reliability growth analysis, there's a specific tool that's often the go-to, isn't there? The one that brings us to the most practical application.
Indeed. For real-world reliability growth analysis, engineers frequently turn to the Duane model, also sometimes known as the Weibull process, especially in this context.
The Duane model.
Yes. It's a specific type of NHPP that is incredibly flexible and very well suited for tracking these improvement trends in repairable systems. The Duane model's power lies in a single crucial parameter, beta.
Beta.
You can really think of beta as your system's reliability speedometer.
Reliability speedometer, I like that.
Here's the profound insight it gives us. It allows us to quantify something previously intangible, whether a complex system is genuinely learning from its mistakes and improving, or maybe it's stuck in a rut, or even actively getting worse. It's like the ultimate report card for your engineering discipline and your FRACAS process.
Okay, a reliability speedometer. That's a fantastic analogy. So what do the different readings on this beta speedometer tell us? This is where it gets really interesting for anyone trying to understand if a system is truly evolving.
Let's break it down. It's actually quite intuitive once you grasp it.
Okay.
First, if beta is less than 1 level 1, this is the sweet spot. This is what you want to see. It means the rate of occurrence of failures, the ROCF, is actively decreasing over time.
Fewer failures.
Fewer failures. They're becoming less and less frequent. This is the clear signal of genuine reliability improvement. It means your systematic process of finding and eliminating the root causes of problems is actually working. You're successfully learning from your mistakes and making the system more robust, smarter, and more dependable.
That's the goal.
That's the goal. Second, if beta is equal to 1, beta equal 1, this indicates that the ROCF is constant. Failures are happening at a steady, consistent rate.
No change.
No change. There's no reliability growth, but also no significant deterioration. The system is stable, but it's not actively improving. It might be a mature system that has reached its stable state, performing reliably but not getting better. This often means your current efforts are maintaining the status quo, but not driving further reliability gains. Maybe the easy fixes are done.
Okay, plateaued.
Plateaued, exactly. Third, if beta is greater than 1, this is a definite red flag, a warning light on your reliability dashboard.
Alarm bells.
Big alarm bells. It tells you that the ROCF is increasing over time. Failures are actually becoming more frequent as the system ages or as new unresolved issues emerge, perhaps due to inadequate maintenance, wear out setting in without proper intervention, or new stresses on the system.
Things are getting worse.
Things are getting worse. This is a clear sign of deterioration and absolutely requires immediate attention and intervention to prevent things from spiraling out of control. It means your system is degrading, not improving.
That makes so much sense. It's like that student learning a new skill analogy again. Initially, they might make lots of mistakes, a hierarchy of, maybe even a beta greater than 1 if they're really struggling or aren't getting good feedback, perhaps.
Right.
But as they practice, and crucially, as they learn from their errors and adjust their approach, their mistake rate goes down, their ROCF decreases, and their beta would hopefully become less than 1.
That's a perfect analogy. The Duane model really helps engineers track that learning curve for a complex system.
But how do they actually get this beta value from real-world data? What's the practical step? How do you calculate the speedometer reading?
They estimate it from the meticulously collected data of fault times. Engineers record the exact cumulative operational time when each fault occurs during the system's operation or testing.
Those timestamps from the FRACAS system.
Exactly. This isn't just a casual log, it's precise timestamps relative to the start of observation or operation. By plugging these fault times, let's call them T1, T2, T3, up to Tn, for n observed faults, and the total observation time T into a specific statistical formula derived from the Duane model.
Some math happens.
Some math happens, yes. It often involves logarithms of the times, but it's a standard calculation. They can then calculate an estimated beta, which we often denote as base, or beta hat.
Betas. The estimate.
The estimate, yes. This initial estimate gives them a powerful, quantifiable idea of the current reliability trend. It's the first tangible step in moving from qualitative observation, I think things are getting better, to quantitative proof. Our beta estimate is 0.6.
And you mentioned confidence earlier.
Right. And beyond just that single point estimate, they use well-established statistical methods, often involving something called a chi-square distribution, which is just a reliable statistical measuring stick for this kind of data to construct confidence intervals around this beta estimate. And that's crucial for making robust decisions.
Okay, so let's take all this theory and put it into practice.
Yeah.
Imagine a real-world scenario, like that brand new signaling system for a busy commuter line. Or maybe that new fleet of high-speed railway cars that just entered service. How do engineers actually monitor its reliability growth and use these beta values?
Well, it starts with that meticulous, continuous observation we keep emphasizing. Every single fault, every anomalous event, every near-miss situation gets logged with its exact time of occurrence.
Building the data set.
Building the data set. This creates the precise input we need for the analysis. Let's consider a hypothetical but very realistic example that mirrors actual engineering challenges. Imagine we've been tracking a new railway system for a specific period. Maybe it's first few months of operation, maybe it's accumulated, say, 10,000 operational hours across the fleet or system.
Okay.
During that time, our FRACAS system has diligently logged, let's say, 158 distinct fault events, each with its precise timestamp relative to the start.
158 events in 10,000 hours.
Right. After gathering all this granular data, we run our calculations using the Dewey model formulas. And let's say our estimated beta, our BIS, comes out to approximately 0.496.
Okay, so FACAS equals 0.496. What does that number immediately tell us? Is that good news, bad news? What's the instant takeaway?
Since 0.496 is clearly less than 1.
Significantly less.
Significantly less, yes. It immediately suggests that our system's reliability is indeed improving. The rate of occurrence of failures is decreasing.
Good news.
Very good news. The system is experiencing fewer failures as time progresses, which indicates that our fault detection processes and, crucially, our fault removal processes, the analysis and corrective actions are working effectively. We're actively learning from each incident, applying those lessons, and making the system more robust over time. This is a very positive indication, especially for a new system finding its feet.
That's a good sign, and certainly reassuring for the engineers and managers. But, as you stressed, in engineering, especially for safety-critical systems like railways, a single estimated value, even if it looks good like 0.496, isn't quite enough, is it? You need to be confident in your findings to know that this isn't just a statistical fluke or random variation.
Absolutely. Confidence is paramount. This is where the concept of a confidence interval becomes incredibly important. We use statistical tools to calculate a range within which the true underlying beta value is highly likely to fall. Typically, engineers use a 90% or 95% confidence level.
Giving a margin of error, essentially.
Exactly. It acknowledges the uncertainty inherent in estimating from limited data. So for our example, if we calculate a 90% confidence interval for our beta estimate of 0.496, the math might tell us that the true beta value likely falls between, say, approximately 0.4396 and 0.5718.
Okay, so between roughly 0.44 and 0.57.
Right. This means we are 90% confident that the true underlying reliability growth rate for this system, based on the data we've seen so far, falls somewhere within that specific range.
And this is where the aha moment for statistical proof of improvement really happens, isn't it?
Yeah.
Because that upper limit tells you so much.
Precisely. You've nailed it. The most critical point here is to look at the upper limit of that confidence interval. In our example, the upper limit is 0.5718.
Still well below 1.
Still significantly less than 1. This provides strong statistical evidence. It tells us that we can confidently reject the hypothesis that the reliability is stagnant beta 1, or even worse, deteriorating beta 1. We're seeing statistically significant reliability improvement.
It removes the doubt.
It removes reasonable statistical doubt. This rigor prevents us from being overly optimistic based on a single number or drawing false conclusions from random noise in the data. You could theoretically have a point estimate for beta that looks okay, maybe 0.9.
Close to 1, but less.
Right. But if its upper confidence bound is, for example, 1.1, you can't statistically prove improvement because the true value might still be 1 or even greater. The confidence interval provides that necessary statistical certainty, giving a robust basis for engineering decisions and claims about improvement. It's the difference between hoping things are getting better and knowing with a quantified level of confidence that they are.
So once you've established this trend of reliability growth and you have that statistical confidence, you can then start to predict the future behavior of the system, which must be incredibly valuable for planning maintenance, spares, operations.
Incredibly valuable. You're essentially using these statistics, these models, as a form of crystal ball, albeit one grounded in data and probability.
A statistical crystal ball.
Exactly. Once we understand the reliability growth trend, its rate, beta, and its statistical certainty, the confidence interval, we can use these models to predict how the system will perform in the future. Critically, this assumes our improvement process, the FRACAS system, the engineering effort remains stable and consistent. If we stop fixing things, the predictions are invalid.
Right, the effort needs to continue.
Assuming it does, a key metric we often predict is the mean time between failures, or MTBF.
MTBF.
Yeah.
Heard that one before.
Yeah, that's a common one. Essentially, this tells us, on average, how long we can expect a system to operate between consecutive faults occurring. A higher MTBF is always better. It indicates longer periods of uninterrupted operation,
Leading to happier passengers and more efficient railways.
That's the direct link. Longer MTBF means better service, lower disruption costs.
So how do these predictions actually work in practice? Do you just pick one number for the future MTBF, or do you get a range, maybe linked to that confidence interval?
You typically look at a range because of that uncertainty we discussed. We can make predictions in a few different ways, each serving a different purpose.
Okay.
We can use our single point estimate of beta, like the 0.496 in our example, to give us a baseline prediction. This is what we might expect under average conditions are most likely future MTBF if the trend holds exactly as estimated.
The middle ground.
Middle ground. Or we could make more optimistic predictions by using the lower end of our beta confidence interval, the 0.4396. This assumes the best case rate of improvement within our confidence range.
The sunny outlook.
The sunny outlook. And then, perhaps most importantly for planning, there are the pessimistic predictions, which use the upper end of that beta confidence interval, the 0.5718. This assumes the slowest rate of improvement we're reasonably confident might be occurring.
Preparing for the worst, statistically speaking.
Precisely.
And I'm guessing that for safety-critical systems like railways, where the stakes are incredibly high schedule adherence, cost, and above all, safety, the pessimistic prediction is king. You always want to plan for the worst-case plausible scenario to ensure safety and resilience.
You're absolutely right. When you're dealing with railway systems or aerospace or nuclear power or any high-consequence engineering where human lives and massive investments are at stake, you always want to plan based on the most cautious, conservative scenario that your data supports.
Makes sense.
So if we're predicting future MTBF for a new train or signaling system, we would typically use that upper confidence limit for beta for key planning decisions, even if it gives us a seemingly less favorable lower MTBF number.
Even if the point estimate looks better.
Even then, this provides a safe, conservative margin for operational planning. It ensures we don't underestimate potential failure rates when setting maintenance schedules, stocking spare parts, or determining staffing levels for repair crews. This is absolutely vital for managing risks effectively.
Can you give us a concrete example of what those predictions might actually look like in numbers, perhaps tied back to our earlier hypothetical system? What do these different MTBF figures tell an operations manager?
Certainly. Let's continue with our earlier example. Estimated beta in 0.496, and the 90% confidence interval is your 0.4396, 0.5718. Let's say we want to predict the instantaneous MTBF 1 year from the start of our observation period. So after 365 days of continuous operation, assuming 247 operation for simplicity here, though you'd use actual operational hours.
Okay, predicting for 1 year out.
Right. Using the optimistic beta, the lower confidence bound, 0.4396, the model might predict an MTBF of over 4 days, let's say approximately 4.4 days between failures at that point in time.
Sounds pretty good.
It sounds fantastic, almost a week between failures. An operations manager might see this and think, great, minimal disruptions expected. Now, using our point estimate for beta, 0.496, the prediction might be around 2.3 days between failures. Still pretty good, suggesting a failure only every couple of days on average for the system. This is our most likely scenario based purely on the estimate.
Right.
But now, using the pessimistic beta, the upper confidence bound 0.5718, which, again, is the safest bet for operational planning, the predicted MTBF at that 1 year mark might be closer to 0.94 days.
Less than a day.
Less than a day between failures on average. This means, statistically, under the most cautious estimate supported by our data, you could expect a failure roughly almost every day across the system being monitored.
Wow, that's a huge difference from the optimistic 4.4 days.
A massive difference. And this isn't necessarily bad news in the sense that the system is doomed, but it's crucial information for planning. This difference in prediction from over 4 days to less than 1 day is absolutely vital.
How so?
It directly impacts planning for maintenance schedules. Do you need daily checks or weekly? How many spare parts do you need readily available? How many technicians need to be on call or on shift for quick responses? What operational contingencies do you need if a failure occurs almost daily?
Right. You plan completely differently if you expect a failure every day versus every 4 days.
Completely differently. You're planning for a scenario where you know you might face a failure almost every day, which forces you to be prepared with resources and procedures rather than optimistically hoping for a failure every 4 days and being caught completely off guard when they happen more frequently. It's the difference between proactive readiness and reactive scrambling.
There's a huge practical implication, and it really highlights the importance of not just the beta estimate, but those confidence intervals. It's not just about what you hope will happen, but what you absolutely need to be prepared for based on the statistical evidence. And it brings us back full circle to something you mentioned earlier, which feels incredibly important. All this sophisticated math and modeling, the beta values, the confidence intervals, the predictions, it's only valuable if the underlying technical processes are sound, right?
That's perhaps the most important takeaway of all, honestly.
You can have the best model in the world, but if the data going in is garbage, or worse, if the actual engineering work, the analysis and fixes, isn't being done properly or consistently, then the model tells you nothing meaningful. Or worse, something misleading.
That's absolutely correct. All this complex math and precise modeling is utterly worthless if there isn't a robust, stable technical process in place for actually finding and removing faults effectively.
The human element.
The human and process element. If your team isn't systematically detecting failures and near misses, if they're not rigorously analyzing root causes using methods like the 5 whys or fishbone diagrams, and if they're not consistently implementing effective, validated changes through thorough change management and regression testing,
then the beta value won't show improvement.
Exactly. Or if it does by chance, it won't be sustainable. No amount of statistical analysis can predict true reliability growth if the fundamental engineering work isn't happening. The data simply won't reflect reality because the reality isn't one of genuine improvement.
The model just reflects the process.
Precisely. It's the human dedication to continuous improvement, the discipline in applying frameworks like FRACAS, the technical rigor in root cause analysis, and the commitment to thorough change management that makes these models meaningful and ensures the data reflects real, actionable reliability growth. Without that foundation, you're just crunching numbers that tell you nothing more than the system is failing, without any real insight into why or confidence that it's truly getting better.
What's fascinating here, listening to all this, is that it's such a perfect blend. It's rigorous engineering discipline, that hands-on work, combined with quite advanced statistical analysis, all working together towards a common goal, making our daily lives smoother, safer, and more predictable.
It really is.
It's a testament, I think, to how meticulous planning and data-driven decisions really build and improve the complex world around us.
Absolutely. The reliability of something as fundamental and complex as our railway systems isn't left to chance, not in well-managed systems anyway. It's built, debugged, and actively grown through meticulous, relentless effort, learning from every single event, every data point.
So to wrap up, we have navigated the fascinating world of reliability growth today. We went from the essential technical measures like that detect, analyze, implement cycle, and the importance of rigorous frameworks like FRACAS and disciplined change management.
The foundations,
all the way to the powerful mathematical models like the non-homogeneous Poisson process, and specifically the very practical Duane model, which acts as our statistical crystal ball, or perhaps our reliability speedometer. We saw how a single parameter, beta, can tell us so much whether a system is truly getting better, staying the same, or getting worse. And crucially, why relying on confidence intervals is absolutely vital for making accurate, safe predictions in the real world.
And it's worth repeating, this deep dive wasn't just about trains, although the railway context provides a fantastic, tangible illustration of these principles in action.
Right.
These very methods, the principles of systematic fault detection, thorough root cause analysis, disciplined change management, and the application of models like the Duane process, they apply to almost any complex, repairable system you can imagine.
Like what?
Oh, think communication networks, power generation plants, large-scale industrial machinery, complex manufacturing lines, even cutting-edge medical devices or the infrastructure behind smart cities. Anywhere you have a complex system that fails, gets repaired, and needs to improve over time.
So the core lesson seems really clear. True reliability improvement isn't accidental or just a stroke of luck.
Definitely not luck.
It's the direct result of a disciplined, data-driven, and continuously improving engineering process. It's about systematically learning from every single failure and near miss, turning every single hiccup into an opportunity to strengthen the system for the future.
Well put.
So perhaps a final thought for our listeners. The next time you encounter a new piece of technology, whether it's a smart home device that keeps getting firmware updates or a new public transport system being rolled out, maybe ask yourself, how is its reliability growing? What might its beta value be telling its engineers right now?
That's a great question to ponder.
It's a simple question on the surface, but thinking about it that way can reveal a tremendous amount about the quality, the longevity, and the underlying engineering excellence or lack thereof of any complex engineered system you interact with.